Welcome back. In this video, I will derive the Michaelis-Menten kinetics and look at how it can describe enzymatic reaction. Enzymes are proteins that speed up biological reactions without being used up, and substances that speed up reactions without being used up are called catalyzers. Enzyme is a special type of catalyzer that is made of proteins that catalyzes biological reactions. For example, sucrase is a digestive enzyme made of proteins that breaks down sucrose into its components of glucose. To illustrate this, we can write the formula for the chemical reaction. So we have sucrase, the enzyme that binds to sucrose. And it breaks sucrose down into two glucose molecules. And the sucrase itself is preserved. This is the overall reaction. To further illustrate this, we can draw a schematic for the enzyme sucrase plus the sucrose, which is broken down into two glucose molecules, and the sucrase is not harmed. Break it down even further to its mechanism. The sucrase first binds to sucrose so that it forms a sucrase-sucrose complex. So we draw it. We have the sucrase with an opening that can bind with sucrose. They add together so that it becomes a whole complex. And then the sucrase-sucrose complex breaks it apart so that goes to sucrase plus two of the glucose molecules. It breaks it apart in the middle so that the sucrase, the enzyme, is preserved plus two of the glucose. And this is the mechanism. Of course, this is a simplifying mechanism for how sucrase works, but this can be generalized to many enzymes. We can generalize this by considering the simplest enzymatic reaction, where we have substrate S that goes to product P by the reaction with enzyme, which is the catalyst. So we have substrate goes to product with the aid of enzyme. And the enzyme is not consumed, but it is within the reaction mechanism. The reaction mechanism would be the substrate binds to the enzyme and forms a complex. And this reaction is reversible and has a forward rate constant of K1 and have a reverse rate constant of K-1. After the complex has formed, it will irreversibly go to the product and release the enzyme. To illustrate this, let's again consider cartoon. So we have the substrate as a triangle, and the product as a circle, and the enzyme as a weird edge shape. The reaction mechanism tells us that substrate plus the enzyme will bind together with a forward and reverse rate constant K1 and K-1 that forms the enzyme substrate complex. And the enzyme substrate complex will form irreversibly through a rate of K2, the product plus enzyme. If we do some canceling on both sides of the reaction, we'll see that the enzyme cancels out and the enzyme complex cancels out, and we're left with substrate going to the product. And therefore, this reaction mechanism could describe the overall reaction. We will describe this simple enzymatic reaction with some simplifying assumptions, and the result is the Michaelis-Menten kinetics. Now let's derive the rate of production, R of P, described by Michaelis and Menten, and determine Vmax and K of M. And we will first consider the reaction mechanism of substrate plus enzyme with a forward rate and a reverse rate of an equilibrium reaction going to enzyme substrate complex. The enzyme substrate complex goes irreversibly through a rate constant of K2 to the product plus releasing the enzyme. We write the rate expression of the rate of production R of P, which is the derivative of the concentration of product with respect to T, should be equal to the rate constant of the final reaction, because P is there, so it is formed at the rate of K2 times the concentration of the intermediate ES complex, and we assume that these are first order reactions, first order elementary reactions. So they obey the rate law of the power law. However, we notice that the concentration of E of S is not measurable. We cannot measure E of S because it is in reaction intermediate, and we cannot know its concentration. What we can measure, let's call it measurables, is the concentration of the substrate, concentration of the product, and the total concentration of enzymes, let's call it E of T or E total. We cannot measure is the concentration of the enzyme currently and the concentration of the intermediate complex. Even though we cannot measure them, we can write indirect formulas to get the concentration of enzymes and the enzyme substrate complex. So how do we get indirect formula for E of S concentration? We do that by writing the rate expression of the rate of production of intermediate. That is the rate of ES, which is equal to the derivative with respect to time of the enzyme substrate complex concentration. You see, in the first reaction, we see E of S appears on the right side, so that we have it is formed at a rate of K1 with the elementary rate law of concentration of S, concentration of enzyme. And it is lost at a rate of K-1 at its own concentration. And for the second formula, we see that it is a reactant, so it is lost at the rate of K2 times its concentration. Now, how do we get E of S though? Here we need to make a simplification called the pseudo-steady-state approximation, or sometimes called the quasi-steady-state approximation. This approximation says that the intermediate E of S are immediately consumed after the production, so the net rate of the intermediate is 0, such that R of ES can be equated to 0. Here we have the pseudo-steady-state approximation. Before we move too fast and solve for E of S, we should also realize that E here we cannot measure. So if we solve for E of S here, we'll have a term that is related to E that we cannot measure. So we will also want to relate E to some other quantities that we can measure, such as S, P, or total concentration of enzymes. Now, to write the concentration of E with respect to other quantities, we can perform an enzyme balance. That is, the total amount of enzyme is constant. So we have the concentration of enzyme total is constant, and it equals to the concentration of E, the enzyme that is available, plus the concentration of enzyme substrate complex. That is the enzyme that is occupied. So enzymes are either occupied or unoccupied. From the enzyme balance, we can solve for E, which is equal to the total amount of enzyme plus minus the already occupied enzymes. And now we have written E in terms of a measurable quantity and a quantity that we're solving for. Now we can substitute the E into the equation and solve for E of S. So we have K1 S times E, and E has a component of total enzyme concentration minus E of S. And then the later part we'll just copy things. Now we can solve for E of S. E of S is equal to, let's break things down. So we have K1 S E of T at the top. And at the bottom, we have everything moved to the right, so they get a positive sign. They have K1 S plus K negative 1 plus 2. Now we have solved for E of S. Because we have solved for E of S, we can substitute this back into the rate expression. So we have R of P equals to K2 E of S. Substitute E of S, so we have K2, then K1, I'm just copying the E of S expression. Whole term divided by K1S plus K negative 1, 2. Here we're essentially done with deriving the Michaelis-Menten kinetics, but we can make some simplifying assumptions so that the terms can group together to make more meaningful interpretation for the reaction kinetics. So from this rate expression, we can introduce some interpretable parameters. For example, we can set a maximum rate of reaction written as Vmax that is equal to K2 times the concentration of total enzymes. We have this term together is the maximum rate. We can also define Michaelis-Menten constant that collects all of the reaction constants. We can also introduce the Michaelis-Menten constant that collects all of the reaction rate constants together, and they collectively define the attraction of an enzyme to its substrate. We can also define the turnover number called K catalytic and set it equal to K2, the rate of reaction of the final step where the complex is turned into the product and releases the enzyme. It is the number of substrates that is converted to product per unit time on an enzyme that is at saturation. Now let's simplify the rate expression by using the Michaelis-Menten parameters. First, let us divide the rate expression by K1 on both top and bottom. So we have the K1 at the top cancels out, so we have K2 multiplied by total enzyme multiplied by S. The K1 cancel out at the bottom plus K minus 1 divided by K1 plus K2 divided by K. And we can see that K2 times E of T is just the Vmax, the maximum rate, multiplied by S. And we have S plus, here we can write it in, because they have common denominator of K1, we can recognize that this whole term is just the Michaelis-Menten constant. So we write it as plus K of M. So now we have derived the Michaelis-Menten equation where the rate of production is equal to maximum rate times the substrate concentration divided by the substrate concentration plus the Michaelis-Menten constant. Now let us do a brief demonstration on how the production rate is related to the substrate concentration. Here I have plotted the rate of production with respect to the substrate concentration in a graphing calculator called Desmos. Here we can explore the effect of changing the parameters on the curve of R of P with respect to S. For example, currently I have the total concentration of enzyme as 5. And note what happens if I increase the total amount of concentration. That increases, the rate of production's maximum increases as well, because V of max also increases. Decreases, the rate of production's maximum also decreases. Now here the K sub n1 is K of -1. Currently it is set to 1. If I increase K -1, you see that the graph shifts right. It shifts right because it increases Michaelis-Menten constant. If I decrease it, the graph shifts left, and the increase is sharp. And the different effect is achieved by changing K of 1. If I increase K of 1, it changes more sharp because it decreases the Michaelis-Menten constant. And if I decrease it, the graph smoothens because it increases Michaelis-Menten constant. If I change K2, it not only affects the Michaelis-Menten constant, but also the maximum rate Vmax. So if I increase K of 2, note that the maximum rate increases and the shape of the graph shifts. If I decrease it, both the shape of the graph and the maximum shift too. Note that I have a special point laid out on here that is labeled purple. And this point is where the x-axis S has a concentration of the Michaelis-Menten constant, where S is equal to K of M. And the y-axis, the rate is equal to the half of the maximum rate. So Vmax divided by 2, which is 5 divided by 2, 2. If I change these parameters, that point also changes, but its expression is the same. We can derive that by looking at the half maximum point. If the rate of production is equal to half maximum, then we can equate it with Vmax S divided by Kmax plus M. The Vmax cancels out, so we have 1/2 Km plus 1/2 equal to S. We solve for S, we have that equals to Michaelis-Menten constant. Therefore, it gives us when R of P is equal to 1/2 Vmax, then substrate concentration should be Michaelis-Menten constant. And from the graph, we have seen that as well. So we have graph Michaelis-Menten constant, the Michaelis-Menten equation, x-axis of S, y-axis of R of P. The maximum here is the Vmax, and at the half maximum point, so Vmax divided by 2, we have the concentration of S is the Michaelis-Menten constant. The Michaelis-Menten equation describes well about the rate of production with respect to the substrate concentration. However, how do we know the Michaelis-Menten constant and the maximum rate in the first place? We determine them using the linearized form of Michaelis-Menten constant and use experimental data to fit to them. We can linearize the Michaelis-Menten equation by doing clever rearrangement. The most commonly used one is called the Lineweaver-Burk equation. From the Michaelis-Menten equation, we first take the inverse of both sides. So we have 1 over R of P is equal to Km plus S divided by Vmax times S. And note that we have a common denominator on the right side, so we can write it out in terms of 2 terms. So we can separate the top. And here we notice that the S can cancel out on the second term. So that we have 1 over Rp is equal to Km divided by Vmax multiplied by 1 over S plus 1 over Vmax. And this is called the Lineweaver-Burk equation. And if we plot this with respect to experimental data, we'll get that on the x-axis, we'll have 1 over S, and on the y-axis, we'll have 1 over Rp. So the measurable here from the experiment is the rate of production and the substrate concentration. and we want to get the Vmax and K of M. Lineweaver-Burk plot is positive. That is because we see that this is y term, this is the x term, and here we have the slope. Here we have the y-intercept. So that we have the slope is equal to Km divided by Vmax. And the y-intercept is 1 over Vmax. So we can first solve for Vmax, then we can get K of M. Let's label this Lineweaver-Burk. Lineweaver. We can also do other rearrangement, but the derivation is not shown here. So for example, here we have R of P is y, and we have R of P divided by S is x. So we have for the Eddy-Hofstad equation, on the x-axis we plot Rp over S, on the y-axis we plot R of P. And we see that the slope would be negative K of M, and the y-intercept is the Vmax. So we have a negative slope, but the intercept we have Vmax, and the slope is equal to negative Km. And for the Haynes-Wolff equation, we have the y is S over R of P, and the x is simply S. We can draw a graph. On the x-axis we have S, the y-axis we have S divided by P for the Haynes-Wolff equation. For this equation, the slope is 1 over V of x, and the y-intercept is K of M divided by the Vmax. Therefore, we have a positive slope, and the intercept is K of M over Vmax. Slope is equal to 1 over Vmax. So we first solve for Vmax, then we get K of M. In this video, I derived the Michaelis-Menten equation using simplifying assumptions of quasi-steady-state approximation. I showed how each of the parameters can affect the shape of the Michaelis-Menten graph, and we can linearize the Michaelis-Menten equation into Lineweaver-Burk equation and use experimental data to fit the equation to get Vmax and K of M.